right, today we're going to take a look at section 9.5, alternating series. So you may or may not have noticed as we've been working so far, but all the sequences and series of things that we've been working on, with all of our tests and everything from 9.2 on, have been hinged on series that have positive terms. And we're going to take a look today at what happens when those terms are not all positive, specifically the case where they alternate back and forth, where they alternate signs. So Theorem 9.14, Theorem 914, says the following. Let a sub n be greater than 0. The alternating series the summation from n equal 1 to infinity of negative 1 to the n times a sub n and the summation from n equal 1 to infinity of negative 1 to the n plus 1 times a sub n converge when. So let's just pause for a moment there and talk about what this is saying. Those two sequences are really the same thing. One of them just has negatives on the even terms, and the other one has negatives on the odd terms. Okay, so this is covering both cases, is what it's saying. The fact that a sub n is positive means that, in fact, it really is alternating. So if a sub n is always positive, and we have the negative 1 times at the beginning, half of the terms are negative, half the terms are positive. They're going back and forth. Okay, so it will converge when one of these things, or all of these things, are happening. So the limit as n approaches infinity of a sub n is 0. Now that's really cool because previously, if their terms are positive, that doesn't always happen, and the harmonic series was a case where we've had that happen, right? The limit is 0, but it doesn't converge. So with an alternating series, the limit being 0 is a sufficient condition when it has one more thing to it. And the second item, and we've seen this one before actually, if a sub n plus 1 is less than or equal to a sub n for all n. Basically, that's just telling you that the terms are decreasing. So if the limit's 0 and the terms are decreasing for the a sub n portion of it, the negative 1 to the n at the beginning makes it sufficient condition enough that it's going to converge automatically. So obviously we've got to do an example so you see how it works, right? Okay, so we're going to do this one first. So we're going to determine the convergence or divergence of the series. And our first example is the summation from n equal 1 to infinity of negative 1 to the n times n squared over n plus 1. So the things that we have to check, first we need to make sure that the a sub n part is really positive. All our terms are positive if we ignore the negative 1 at the n part. And then the second thing we would be looking at is if the limit is 0. And then the third thing, I know they're numbered 1 and 2 because the other one's in the conditional part at the beginning, but is to confirm that it's really decreasing. And we've seen the decreasing trick, but we've only seen it once, so it's still probably something that's not quite as familiar to you as some of the others. So let's start with the fact that this is positive. So I'm gonna call this 0. This condition is 0. So we're going to look at condition number 0, or A if you wanted to label it A. So is this sequence always positive? The second part, n squared over n plus 1. Is it positive? Yeah, all these values are positive. These are greater than 0 for all n that are greater than or equal to 1, right? N is 1, so these are all positive terms. So that part's satisfied. Usually that part's satisfied pretty easily, okay? But it's something you should look at just to make sure. The next issue has to do with the limit. So we're going to take the limit as n goes to infinity. And again, we're ignoring the part with the negative 1 to the n. It's just the other part that we're talking about. N squared over n plus 1. So how do we confirm that this goes to 0. What's our next step? What's our trick? What have we done? We do it every time the same way. Yeah. So we're going to multiply by the reciprocal. Let me move that one down a little bit. And 1 over n squared would be just fine. So if I multiply by 1 over n squared, the limit will stay as n goes to infinity. On top I have 1. What's on bottom? Yep, 1 over n plus 1 over n squared, right? That 1 gets multiplied by the n squared, 1 over n squared as well. Okay, so what happens as each of these pieces have n go to infinity? Yeah, those go to 0. So we're just going to write that in. This goes to 0. This one goes to 0. So I end up with what value? What happens when I have a 0 on the bottom? Let me say it that way. It's undefined. It's an infinite limit, right? So this is approaching infinity itself. Basically, we're trying to divide something by 0. When we do that, we get something that's either positive or negative infinity. This one would be positive because our terms are positive. And in particular, that tells you it's not 0, right? And because it's not 0, what does that mean? It diverges. So as soon as you get one of these conditions to fail, you're done. This one diverges. By the alternating series test. We're done. Okay? So if you get this to go to infinity or some other number, could have been, 2 or something like that, we'd still have it diverging. So we would be finished. Okay, so let's try another one. We'd like to check all the conditions, right? Of course. Okay, so the next one we're going to do is the summation from n equal 1 to infinity of negative 1 to the n to e to the negative n. So the a sub n part is the part here at the end. So my a sub n is 2e to the negative n. And there might be a better, maybe more helpful way of writing that. How else could we write 2e to the negative n?
2 over e to the n.
Yeah, 2 over e to the n. Okay, so again, the first condition 0 if you will, 2 over e to the n. Is it positive?
Yes.
Yeah, this is greater than 0. And again, if you remember your graph of e to the n, or e to the x, it looks like this. So we're on the right-hand side of the graph. Over here, these are all positive values. So I'm dividing by positive values. A positive divided by positive is positive. So that's fine. So it's definitely that part we get for free. The next part is the limit as n goes to infinity of 2 over e to the n. Okay, so what happens on this? What is that limit? It approaches 0, yeah, because the denominator is approaching infinity, right? E to something getting infinitely large is another infinitely large value. So this actually equals 0. Let's see what else wrote down here. Oh, that's something else. We're not there yet. All right, so that's condition 2, right? We had to have a limit approaching 0. And then the third thing is that we need to make sure it's decreasing. So this is the trick that we did before about checking to see if something is decreasing, is that we tried to create the ratio of a to the n plus 1 over a to the n. Do y'all remember that? Okay, that's going to create for us an equation using our a sub n and our a sub n plus 1 that we're going to be able to manipulate. So a sub n plus 1 would be 2 over e to the n plus 1, and a sub n would be 2 over e to the n. That's awfully large. Okay, is that good? All right, I don't really want it written like that. That's kind of messy, so I'm going to write 2 over e to the n plus 1 times e to the n over 2. And what do we notice being able to simplify? We'll do the easy one, 2's. Anything else? Close. The e to the n will simplify. Yeah, so this piece right here, e to the n plus 1, can be rewritten as e to the n and e to the 1, like that. So across the diagonal, the e to the n part will simplify. So right now I have a sub n plus 1 over a sub n. And this right now on the top has e to the n. And on the bottom I have e to the n times e to the 1, or just e. That's what I have at the moment. So the e to the n's would cancel. Yeah. So I'm left with just the e in the denominator, 1 on top. And if I cross multiply, this will now give me e times a sub n plus 1 equals a sub n. Okay, is that all right? So what is that telling us about a sub n if a sub n is a sub n plus 1 times e? A sub n plus 1. Did I write that down? Is smaller. Is bigger. Hang on. Yeah, it's bigger. I just have my sign in my notes wrong. Yeah, a sub n is, well, I did it. Is bigger. Oh my goodness. Did I get it right? Finally? Yes. So a sub n is bigger than a sub n plus 1 because it's a sub n plus 1 times e, and e is bigger than 1. Yeah, great. Should probably get that fixed here. Okay, so that's the last condition, right? The third one, or it said number 2. A sub n plus 1, not n plus n. A sub n plus 1 is less than or equal to a sub n. So we have the third condition. All right, so we have the ability to say that this converges. So what will that look like? So we would talk about the fact that the limit of our original, I'm sorry, not the limit, the summation from n equal 1 to infinity of negative 1 to the n times 2e to the negative n converges by the alternating series test. I'll abbreviate. You can too if you'd like. Alternating series test. Because those conditions were met, right? A sub n is greater than 0. The limit of a sub n as n goes to infinity is equal to 0. And a sub n plus 1 is less than a sub n. That's our conclusion. Okay, is that all right? So it's the same 3 conditions every time. If one of them fails, then you're done and it diverges. If they all satisfy, then we write a statement similar to this at the end, and we're finished. All right, so sometimes, however, we may have terms that are some positive and some negative, but they're not exactly alternating, right? Like you might have 2 negatives and then 1 positive, and then you have another negative and 2 positives. So they fluctuate between positive and negative, but they're not consistently going back and forth. So I'm going to write that down. Sometimes a series, and I'll give you an example too, may have both positive and negative terms. But not be alternating. For example, the summation from n equal 1 to infinity of sine of n over n squared. So if I were looking at this particular one, it would look something like, I'll move it to the next part. Like this, it would be sine of 1 over 1 plus sine of 2 over 4 plus sine of 3 over 9, etc.
Degrees or radians?
Always going to use radians when we're working in calculus. Yeah, thanks for asking for that too. So if you do have your calculator set up somehow, like radians is what we're working with. Okay, but these are not nice sine values, right? Like these aren't pi and pi halves and things like that, right? If it was actually like pi values, right, it went from 1 pi to 2 pi to 3 pi, it could actually alternate, right? It could just go back and forth between 1 and -1, and it could be an alternating series. But that's not what we have here. We have these random values and radians around the unit circle. Some are positive, some are negative, depending on which quadrant we're in, and so forth. So this has both positive and negative terms. But is not alternating. So one way to gain some information is to consider absolute values. So for this one, we're talking about the summation from n equal 1 to infinity of the absolute value instead of sine of n over n squared. Okay, so we talked about direct and indirect direct comparison and limit comparison tests last class period, right? So thinking about that direct comparison test, so by direct comparison, if I had sine of n over n squared, it would be less than or equal to 1 over n squared, wouldn't it? And we talked about this from the squeeze theorem perspective back in 9.1. I think it was 9.1. And that's happening because sine of n itself on top is oscillating between -1 and +1, so all the values are going to be absolute value-wise between or less than the value of 1. And then by p series, the summation from n equal 1 to infinity of 1 over n squared converges, right? So the summation from n equal 1 to infinity of the absolute value of sine of n over n squared also converges. Now, that doesn't exactly tell us what happens if we don't have the absolute values, but it has a related feel to it that we can make some information about. And in particular, it leads us to talking about something called absolute convergence. Oops. Okay. So Theorem 9.16 is our theorem for absolute convergence. And it says the following: if the series, and we're just going to leave the limits off because it doesn't matter, if the series absolute value of a sub n converges, beautiful things happen. Then the series, the summation of a sub n without the absolute values, also converges. So what this tells us about this sine of n over n that we started with back up on the earlier part of the screen is that this thing will automatically converge because its absolute value converges as well. So we can kind of ignore the fact that it oscillates in this, irregular way. It doesn't matter because we can take the absolute value of these things and show that they converge. Okay, so definition, building upon this idea of absolute convergence, is the theorem of absolute convergence, is actually how we define absolute convergence. So two-part definition. The summation of a sub n is absolutely convergent when the summation of the absolute value of a sub n converges. That feels almost like circular definition, right? It's absolutely convergent when the absolute value of it converges. So they're going in together. But the reality is that just because the absolute value diverges doesn't necessarily mean that it's going to diverge. So when you have the summation of a sub n, another option is that it's something called conditionally convergent. So this one is absolutely convergent. Conditionally convergent when the summation of a sub n converges, but the summation's absolute value of a sub n diverges. And I can give you a really quick example that we've already encountered of one that works like this. So this isn't an example where we have to work through very much, but just to give you an example of the definition. If we had the summation of -1 to the n of 1 over n, like this, and we compared that to the summation of 1 over n, this guy would actually, let me write it this way. If I took the absolute value of this summation from 1 over n would diverge, correct? This is the harmonic series. This part diverges, so the absolute value diverges. But if we actually took it like this would converge by the alternating series test. How do I know? Well, because it met those conditions. 1 over n is always positive. 1 over n would be actually decreasing, right? Its terms would be decreasing, and the limit of 1 over n as n goes to infinity is 0. So this is an example of a conditionally convergent. So what that tells you is that the summation from n equal 1 to infinity of 1, I left off my -1 to the n, the -1 over n, not only is it convergent, but it is conditionally convergent. It's not absolutely convergent. Okay, so let's actually do one that's not quite so straightforward as that. We have a couple of them, actually. So we're going to determine, I feel like the directions are always the same, determine whether the series converges, but we're going to add in a little bit more, converges absolutely, conditionally, or diverges. So we now have 3 options, not just 2, right? Okay, so our first example of this is the summation from n equal 1 to infinity of -1 to the n plus 1 over n squared. And remember, the n plus 1 or the n being the exponent is irrelevant. That doesn't change anything at all. Okay, so what do we test? Well, we test whether the absolute value of this converges. So the summation from n equal 1 to infinity of the absolute value of -1 to the n plus 1 over n squared. So if I take the absolute value, how does this simplify this terms inside?
Just 1 over n squared.
Yeah, It just eliminates the negative 1 to the n plus 1 part. So this is just 1 over n squared. And I don't even need to have the absolute values anymore because the n squared is positive, right? So 1 over n squared is positive. All that's good. What do you know about this series? Does it converge or does it diverge? It converges. Do you know why? Yeah. So this converges. And if we're saying it converges, we need to say why, like I asked Aaron. So this converges by p series. So we can actually talk about what happens to the series we started with. So the summation from n equal 1 to infinity of negative 1 to the n plus 1 over n squared does what? How does it converge? Absolutely, yeah. I was going to say absolutely or conditionally. Yeah, it's absolutely because its absolute value converged. It converges absolutely. Easy enough? Okay, polynomials are really friendly, so let's do something that's not a polynomial. Before I turn my page, let me give you a second. Some of you are still writing. Okay, we're going to use the same directions. This is number 4. We're going to do the summation from n equal 1 to infinity of negative 1 to the n over n natural log of n. Okay, with those directions, the step at the beginning is always the same. We're going to stick absolute values around this thing and see what happens. So my summation from n equal 1 to infinity of the absolute value of negative 1 to the n over n ln n. And again, what happens to that expression?
1 over n ln n.
Yeah, 1 over n ln n. So we're no longer going to be able to use the p series like we did on the last one. How can we decide if 1 over n ln n converges? What test seems reasonable to try?
Integral.
Yeah, the integral test is a good one. So let's change this into an integral to determine if it will converge or not. So this is 1 over, and I'll switch them out for x's. So this is x ln x and dx. All right, so what kind of integral would we need to be, what kind of integral test would we need to be using for this next, or integral process? How do we integrate this? You guys have done this one recently.
Substitution.
Yeah, it's use substitution. So what would u be? ln x and du is 1 over x dx. So this will get rewritten as, and I'll leave my limits of integration off for the moment, 1 over u du. Is that okay? What's the antiderivative of 1 over u? Yeah, ln u. And u is ln x, so this becomes the natural log of the natural log of x, like that. And I can put my limits of integration back on. It's not infinity like that. Let me put the limit in front. So this is the limit as, let's use r. Limit as r goes to infinity of r, and we have 0. Was it 0? No, it was 1 down here at the bottom. So what is the limit as r goes to infinity of the natural log of r minus the limit, well, the natural log of 1? The right symbol there. Okay. So what do we get at the first part? What is the limit as n, or as r goes to infinity of the natural log of r? Yeah, it's infinity. So this piece right here is infinity. The natural log of 1 is actually what? You know? What's the natural log of 1? Let's start that one. What is the natural log of 1? It's 0. And we run into a problem because this one then becomes natural log of 0, which is undefined. So we have an undefined value here. This whole limit does not approach a number. That's the point, right? This does not equal 0. It doesn't equal 0. So it's undefined. It's actually negative infinity, by the way. So if you really wanted to write it out more thoroughly, this is infinity minus negative infinity, which is just something that's getting infinitely larger more, right? It's infinity plus infinity or something of that nature. So this is not equal to 0 either way. So what does that tell you about this? It diverges. So this diverges. So what does that mean? Well, if you take a look back over here, where were we? Here. It says it's absolutely convergent when the summation of the absolute value converges, and ours doesn't. Correct? So it says if we have, I shouldn't say it that way. It doesn't say for sure that we know it diverges. It could still be conditionally convergent, right? So if you want to think in terms of like worst case scenario, like work-wise, we're in it. We got the absolute value to be non-convergent, to be divergent. So we still have to do more testing to figure out now, is it conditionally convergent or is it divergent? When it converges like this, right, absolutely, that's the easy case. Okay, so what this tells us is this does not converge absolutely. But it's an alternating series. So it could converge conditionally by the alternating series test. So that's the one we need to go back to next. So, okay, well, it doesn't converge absolutely. That would have been very nice, and it didn't work. So now we got to go back and see if it maybe converges conditionally by checking it out just as an alternating series as its standalone piece. So I got to switch screens because I'm out of space. Let me write this at the top of our screen, though, for where we are. So this is where we are, continued. So we can take a look at those three conditions. Condition number 1, A sub n. So A sub n is 1 over n ln n. And if n is greater than or equal to 1, is this positive? Yeah. So this is greater than 0, so that's the first, like step 0 check. Step 1 then is to find out what the limit is as n goes to infinity of 1 over n ln n. So what is the limit as n goes to infinity? Yeah, you're right, Jubal, it's 0, right? We're getting something infinitely large on bottom times something else infinitely large on bottom. So we've got lots of infinites going there. It's 0. And then we should say second step, or third step really, but is to confirm that a sub n plus 1 is greater than or equal to a sub n. So what happens when we have these values, 1 over n and natural log of natural log of n, 1 over n natural log of n? Will it get increasingly smaller every time? Yeah, it works. So this one also checks out. So all three of these things are checking out. So by the alternating series test, the summation from n equal 1 to infinity of negative 1 to the n over n ln n converges. So what that tells us is that the summation from n equal 1 to infinity of negative 1 to the n over n ln n is conditionally convergent. Now, could we have been asked the same question and just asked, is it convergent or divergent? Of course we could. But our directions had three possible answers. The three possible answers were absolutely convergent, which we ruled out, and then conditionally convergent and divergent. And so now we've actually found that it was convergent, and since it wasn't absolutely convergent, that means it's conditionally convergent. Any questions on that? Okay, we've got one more example. All right, the summation from n equal 1 to infinity of negative 1 to the n plus 1 times 2n plus 3 over n plus 10. Okay, process starts the same, directions were the same. We look at the summation from n equal 1 to infinity of the absolute value of negative 1 to the n plus 1 times 2n plus 3 over n plus 10. And this is the same as the summation from n equal 1 to infinity of what? To n plus 3 over n plus 10. Okay, so what do you know about this series? How could we go about deciding if it's convergent or divergent? The which one?
Test or
It's got a different name for it. We were right.
nth term?
The nth term test. The nth term test will work really well. So if we use the nth term test for divergence, so the clue to thinking about that on this is to remember that the part here that really matters is 2n over n, right? That's dominating everything, and 2n over n is equal to 2. So this is actually leveling off like at a horizontal asymptote of y equal to 2. That's not tanking at 0. So we're continually adding 2 lots and lots of times forever. No way that that's going to eventually converge. So if we consider the limit as n goes to infinity of 2n plus 3 over n plus 10, and we multiply by that 1 over n that we've seen before, this will give us the limit as n goes to infinity of 2 plus 3 over n over 1 plus 10 over n. And each of these pieces at the end will do what?
Go to 0.
Yeah, they'll go to 0. So this is equal to 2, which does not equal 0. Right? So by the divergence test, or the nth test for divergence, if you will, it's the same thing. By the divergence test, the summation from n equal 1 to infinity of 2n plus 3 over n plus 10 diverges. Now again, that puts us in the same position that the last one did. It fails to converge absolutely. That doesn't necessarily mean it fails to converge, right? We don't know. We have to do more testing, but it's definitely not converging absolutely. So the summation from n equal 1 to infinity of negative 1 to the n plus 1 times 2n plus 3 over n plus 10 is not absolutely convergent. Okay, but it's an alternating series, right? Okay. but we have an alternating series. So we continue back to looking at it from that perspective. I'm going to squeeze it all on this slide because we've written it all down at this point. All right, so we can consider those three conditions. First condition, a sub n. So a sub n is 2n plus 3 over n plus 10. Is it greater than 0? Yep, all positives everywhere. There's no negatives going on, so that one checks out. The first true step, the limit, as n goes to infinity, of 2n plus 3 over n plus 10. We already did this. What is this limit?
2.
It's 2, right? And I'm just going to write by above. Normally we have to show it, but we've already done it. There's no reason to do it twice. It's equal to 2. In particular, 2 is not 0. So what does that tell you? It diverges, because that's what the alternating series test says. So this diverges. And it's diverging by the nth test, the nth term test for divergence, whatever it's called. I'll abbreviate it that way, divergence test. So what that tells you is by the alternating series test, the original alternating series as well will diverge. So we've seen an example of each one of these three outcomes happen. The first one was absolutely convergent, the second one was conditionally convergent, and this one is divergent. So by the alternating series test, the summation from n equal 1 to infinity of negative 1 to the n plus 1 times 2n plus 3 over n plus 10 diverges. Okay, all good? Okay, I have we don't really have a lot of time to get at the board, so I won't send you there today because you'll be there like 2 minutes and then you'll just get a problem written up there, get a problem written on the board. But these are the problem numbers. So I think it's page 629. If I have the page numbers wrong at some point, please forgive me. You know which section you're in, so you can probably figure it out. The problems we're going to look at are 10, 13, 16, 19, 22, and 25, and then 41, 44, 47, 50, and 53. All right, so that's the written work part. You've got the web assigned part as well. When we get to 9.6, we'll have a little bit of a breather. We're going to do a lot of board work when we get to 9.6. It's a little bit shorter of a lesson. We're going to have a lot of board work on Friday and on Monday. So you're going to have a lot of practice at trying to decide which test do I use when. That's our goal for those 2 days.